now we are going to look at if this graph is continuous at x equals 2. So again, at x equals 2, we're kind of looking right here, the x value is 2. So first we want to figure out if f of 2 exists. So that's always your first go-to. We have to figure out, does f of 2 exist? Well, f of 2, remember this closed circle, that's where I'm looking. So it is 2. So f of 2 equals 2. So yes, f of x exists. So that is a good start. Okay. Now we need to see if it meets the other condition for continuity. And that other condition is that the limit exists. So we're trying to find the limit as x approaches 2. Now remember, technically what you're doing here is you're taking a left limit and a right-hand limit, but you don't need to show that work if they give you a graph. So here, we want to find the limit as x is approaching 2. So we're going to come from the left. And if you come at it from the right, what is the limit? Well, the limit is approaching 1. So we would say that the limit as x approaches 2 of f of x equals 1. Well, here's the problem, okay? And again, I'm just going to kind of write that over here because I'm running out of 2. We would say that this is not continuous because f of 2 does not equal the limit. And that third condition for continuity said that the limit and the evaluation had to be the exact same thing. So since these two are not the same, we would say that this is not continuous. We would say no. Okay? Not continuous. It is discontinuous. Okay, so it is not continuous at x equals 2. Okay. Let's take a look at x equals 1. So again, the first thing you want to do is evaluate. So at x equals 1, you're right here. That's where the closed circle is. So your y value is 1. So you would say that f of 1, okay, so we say that f of 1 equals 1, okay? Now we want to find the limit as x approaches 1. And remember, if you're given the limit from the right and the left, with the graph, you do not need to show it. You are kind of taking both those into consideration. So from the left, so as I approach x equals 1 from the left, looks like the limit there is 0. When I approach it from the right, looks like the limit there is going to be 1. Well, if from the left I'm going to 0, and from the right when I approach I'm going to 1, that means that the limit there does not exist. So you would say that the limit f of x here does not exist. So right away you know that that is not going to be continuous because the second rule said not only did f of a have to exist, but the limit has to exist. So here the limit doesn't even exist, so it definitely cannot be continuous. Okay, now we're still looking at the same graph, but this time we're going to see if the graph is continuous at x equals 4. So the first thing we want to do is evaluate the function at 4. So let's see, at x equals 4, we are right here. It was a closed circle, so that's going to be a y value of 1. So when we evaluate the function, we get 1. And next we need to take the limit as x approaches 4 of the function. So again, when we're taking the limit, you need to consider the right-hand side and the left-hand side. You don't need to show that work written out because there is a graph. Now here, this is an interesting one because look, this is an endpoint. So here you only can take into account the one-sided limit, and that limit is approaching 1 as well. And so you would just kind of indicate that by saying that you approach it from the right. So again, we put that little plus sign up and to the right of 4. And we know that that is also 1. Since these two things are the same, that makes me happy. Okay, that says that this function is continuous. Okay, yes, it is continuous. And so the last part there, it says f of x is continuous, ... So basically, we just want to know the interval. We don't start until 0. So we say that it's continuous from 0 to 1, union 1 to 2, because there was a discontinuity at 1 there. We already concluded that right here. Okay. And then another union, I'm going to have to go down here because I ran out of space, from 2 until 4, and you can use a bracket there because that 4 is the endpoint. And that is the interval of continuity for this function. All right, let's take a look if you're not given the graph. Oh, I'm sorry. Sorry, I was getting a little bit ahead of myself there. So on the last slide, we did say that there was a couple places where this was discontinuous. So we said at 1 it was discontinuous, and also at 2 there was a discontinuity at 2. So now we're just kind of looking at the different types of discontinuity. Okay? So in this first example, there is a vertical asymptote. So when you have a vertical asymptote, we're going to call that an infinite discontinuity. So these are just the different types of discontinuity. So I might say, oh, there's an infinite discontinuity, or oh, there's a removable one. If you remember that matching activity that you did last class and the one before that, the descriptions had talked about removable discontinuities and what those are, so we'll take a look at that. So again, in this first graph here, there is this vertical asymptote right there, so we say that that is an infinite discontinuity there. And then in the next graph, it's kind of hard to see on your paper, but you have this line and there's an open circle right there, and then up here there's a closed circle and it takes off to this side, okay? So if you can't see that on your paper, go ahead and draw that in there. This is actually called a jump discontinuity, okay? Basically think of this as your one-sided limits are not equal, right? The limit is I'm kind of approaching this one here, like the limit is I'm going from the left is going to be 0, but if I go on this line, I was approaching 1. So here the one-sided limits are not equal. You can make that note. One-sided limits are not equal, okay? So that's called a jump discontinuity. And then the third type of discontinuity we have is called removable. And again, that word may look familiar from that activity from last class. Okay, removable. Okay. And so removable discontinuity, I have two pictures here. These are both examples. So notice on this graph, there is an open circle there, and there is no filled in. And then on this graph, there's an open circle there and filled in. So I just wanted to show you that a removable discontinuity could be the whole by itself, like in this one here, or like here, there is a hole, but then there's also a point. Okay, so either one of those are considered a removable discontinuity. Okay, so those are your three types of discontinuities. We can go to the next slide. And so now you have a chance to try it. And on this one, so we're doing just what we did on the graph, but only if it is discontinuous, you have to say the type of discontinuity that it is. Okay? So it's just like before, but only now we're kind of taking it a step further and we're saying, well, if it's not continuous, then it must be discontinuous. And if it's discontinuous, I want you to pick one of those three types of discontinuities and identify it as such. So let's see. We're looking first at where x equals negative 2. So at x is negative 2, right? So I'm kind of looking, let's see, right here, that was the closed circle. Okay, so first I need to evaluate, because remember, to test for continuity, first you need to figure out if f of 2 exists, or f of negative 2 exists. So sure, here, f of negative 2 does exist. In this case, it's positive 2. But the limit also has to exist, right? Number 2, in the rules of continuity said that the limit has to exist. Well, here's the problem. If I'm approaching from the left, the limit is 2. If I'm approaching from the right-hand side, the limit is negative 1. So here, the limit, as x approaches negative 2 of f of x, does not exist. So if that's not met, then it's definitely discontinuous. So we would say that it's discontinuous. So it is discontinuous, okay? And the type of discontinuity. Well, looking at that, at negative 2 there, okay, what type of discontinuity is that? There's not an asymptote, so it's not infinite. This one, you literally are jumping from one point to the next. So there's like literally a break in the graph. The one-sided limits are not equal. So this one is going to be an example of jump discontinuity there. All right. So then let's take a look at x equals 0. So f of 0, the first thing we always do is evaluate. So f of 0 equals 1. So that's good. Okay, so I'm looking right here at x equals 0. The function is at 1. And now we need to find the limit. So the limit as x approaches 0 of f of x. Remember, when you're taking this into account, you have to take into account the right-hand limits and the left-hand. So if I'm approaching from the right, my y value is getting close to 1. So I'm approaching from the left I'm getting close to 1, from the right I'm getting close to 1. I said that backwards. Either way, it's 1. Since those two numbers are the same, that makes me happy. It's continuous right there. So we would say that this is continuous at x equals 0. And now we can move on to the third one. All right, so at x is 3. So I want to first evaluate f of 3. So at f of 3, the function does exist. Notice this closed circle down here. Okay, so at f of 3, I get negative 1. But now the limit, okay, so the limit as x approaches 3 of f of x, let's take a look at what the limit is. Well, when I approach 3 from the left, looks like my y value is getting close to 0. When I approach 3 from the right, the y value is getting close to 0. So my limit is 0. So even though the limit exists, when I evaluated the function, I got negative 1, and the limit was 0. So those two things do not equal each other, right? That makes me sad. Okay, so you would say something like this. You'd say f of 3 does not equal the limit as x approaches 3 of f of x. And so then we would conclude that it is discontinuous. Discontinuous at x equals 3. And what kind of discontinuity is it? Well, there's a hole there, so it would be a removable discontinuity. Okay, perfect. All right, so given a graph, it's kind of easy. In fact, some of you might be wondering, do I have to show all that work when I'm given the graph, right? It kind of seems easy for it. Well, I'd like you to show the work for it, but you definitely need to show the work when it's given to you algebraically, when it's kind of given to you as this piecewise without the graph, okay? So without the visual representation, we are going to have to kind of plug in to get the answers, okay? You'll have to kind of plug in here to get the answers. The first thing you want to do is plug in this case, you're going to plug in at 2, right? So f of 2. Remember, this greater than or equal to means when I'm plugging in at 2, that's the equation that I have to plug into, that second one. So to evaluate f of 2, right, that's 2 times 2 minus 1. Okay, so that gives me a 3. Okay, so does f of 2 exist? Yes. So now I get to say, does the limit exist? Here's where, remember, you need to show the left and the right. If they don't give you the picture, then you need to show it. The limit as you approach 2 from the left of f of x equals some number, and you need to say the limit as you approach it from the right of f of x equals some number. So let's see. If I approach it from the left, I'm plugging into the top equation, okay? So when I approach it from the left, I get 3. When I approach it from the right, I'm plugging into the bottom equation. So when I plug in a 2 into that equation, I also get 3. So that tells me that the limit does exist. So I should be able to conclude that the limit as x approaches 2 of f of x equals 3. So now I know that the limit is 3, and when I evaluated, I got 3. So since those two are the same number, we can conclude that this is continuous at x equals 2. Okay, because the limit and the evaluation are the same